Hello everyone, I am Yikai Wang, a third-year PhD student with supervisor Dr. Yanwei Fu from School of Data Science, Fudan University. Following Yanwei's talk, I will spend 20 minutes to give the more detailed explanation on sparse learning for noisy data labels part, mostly from the statistical perspective. I will introduce a simple yet effective framework for noisy data detection with applications in different vision tasks. First, I will introduce what is sparse learning for noise data detection. What is noise data? It may be the red apple surrounded by green apples. It might be the data for more than 3 standard deviations from the mean value, or it might be the point that are far away from the curve. Generally, noise data or outliers are the irregular data compared with the majority of the dataset. In particular, in label space, noisy data mainly refers to the mislabeled data. These mislabeled data may come from many aspects. For example, if the labels are randomly cropped, then some irregular labels will lie in the label space. Our humans are inevitable to make mistakes, so our annotations are not so credible. In some research areas, people will use the research engine to get training data. However, as an example, if you search Shogun in Google, it may return a historical figure or game character, but usually not the both are expected. Also, we may collect some complex or confusing images that are hard to distinguish. For example, this is a dog but looks like a cat. What can we do to identify these noisy data in label space? Here, to identify these noisy labels from the training set, we propose to use a simple linear system to model the relation between network features X and one-hot labels Y. This linear system is known to be sensitive to noisy data. That is, the solution of beta is not stable as it may be influenced by even a single outlier. But actually, this is exactly what we want. Why do we use this linear system? For an ideally trained network, we have a softmax linear relation between feature vector and one-hot labels. If we approximate this by dropping the softmax operator, we can get the linear system. This is a weak approximation, but this is helpful for our target. Specifically, we introduce a noise data indicator, gamma, to represent the noisy data explicitly. For clean data, the linear relation is strong, thus we should have a small or even zero gamma. If the data is noisy, a large gamma will be returned by the linear model to better fit the noisy feature label pairs. Basically, gamma can be regarded as a residual predict error. This is a baseline method to identify noisy data in the training set. However, these raw residuals fail to detect outliers at leverage points. A better way is to use a leave-one-out externally studentized residual to test whether the predicted residual is large based on the other observations. This is equivalent to test whether gamma equals to 0 in this equation. However, this can only be solved when there is a single outlier. When there are multiple outliers, we have two additional problems to solve. First is masking. Multiple outliers may group together to mask each other to be undetected if we only leave one of them in the statistical testing. The other is swapping. Multiple outliers may result in large T for clean data, leading to a false discovery of outliers. Thus, we can solve the whole indicator matrix for all training data at the same time, leading to this equation. Our target is to solve gamma using all the training set and identify the noisy data based on the gamma. As we said above, those non-zero gamma is regarded as a noisy data in the training set. To ensure this, we add a sparse penalty to gamma, leading to this objective. Now, the objective have two unknown parameters, beta and gamma. But we only care about the solution of gamma, and we don't care about what beta is. Further, beta is known to be sensitive to outliers, so we first solve beta with gamma fixed. Then we can use the estimate of beta to the objective, leading to this simplified objective. With further simplification, we give some notations and we can translate the objective into this one, a standard linear regression. Now, the only problem is how to choose the sparse coefficient lambda. A number of methods for determining lambda exist, but none is suitable for our formulation. For example, some historical rules on setting the lambda are popular in existing models such as the M estimator, where sigma hat is a Gaussian variance set manually based on human prior knowledge. However, setting a constant lambda value independent of this set is far from optimal, because the ratio of outliers may vary for different cross-sourced datasets. Cross-validation is also not applicable here because it can only optimize part of the sparse variables while leaving those held-out validation set undetermined. But this validation set is also noisy. Some data adaptive techniques such as scaled lasso and square root lasso typically generate overestimates on the support set of outliers. Moreover, they rely on the homogeneous Gaussian noise assumption, which is often not valid in practice. The other alternatives like AIC and BIC are often unstable in outlier detection lasso problems. Thus, it is very hard to choose a proper lambda in advance. This inspires us to sequentially consider all available solutions for all sparse variables along the regularization path by regarding the solution of gamma as a function of lambda. When lambda turns to infinity, gamma will turn to zero. In this path, with proper penalty, for example, the row-wise L2 vector norm, gamma will vanish row by row, that is, instance by instance. Then we can use lambda where gamma turns into zero to rank the data and denote the last vanished instances as noisy data. Fortunately, this solution path can be generated by the GLMNet algorithm. This is a visualization of the solution path. The red line is the most credible data suggested by our algorithm. Intuitively, we are finding the x-axis, that is, the norm of gamma vanishes. In summary, our proposed framework, instance credibility inference, assumes a linear relation between network features and one-hot labels, and we use an explicit noisy data indicator gamma to represent the noisy data. We simplify this linear regression model with gamma to linear regression model of gamma. and solve the solution path of gamma to rank the data and select the clean data for training, or in other words, identify and remove the noisy data. As we are still statistical method, we have very nice theoretical properties to identify the noisy subset, that is, the noisy set recovery. A problem is, when will the model identify all the outliers? Our results based on the model selection consistency of Lasso model. We gave 3 conditions here, and we just translate these conditions into English. If we have C1, we can get a unique solution. If C2 holds, clean data and noisy data are diverged to some extent. If we have C3, the error is large enough to be identified from random noise. With these conditions, we can get the following theorem. That is, if we have large lambda and we have C1 and C2, then the noise set identified by Ci is a subset of Grant-Scholes noise set. If further we have C3, ICI will identify all the noisy data. As our theory mainly designed on the assumption of sub-Gaussian noise, we test by running 2,000 random tasks to check whether this holds in practice. The simulated distribution of noise can be roughly combined with 3 Gaussian distributions, which verify that our assumption is reasonable in reality. Now we introduce some applications of sparse learning in noisy data. We first introduce sparse learning in feature learning problem. Feature learning aims to learn a robust model with only a few training data available. If we consider the annotation cost, feature learning lies between unsupervised learning and learning from noisy labels, since we only need to annotate a few training examples. But it is not just training with a few data. For example, the standard binary classification needs a lot of labeled data to model the decision boundary. When we have only a few training data, the decision boundary is very different as we only have access to little information about the two classes. But feature learning aims to get the decision boundary trained with many labeled data using only a few labeled data. This requires additional prior knowledge, like pre-trained with related datasets or with noisy unlabeled data. In industry, it is reasonable and cheap to collect noisy unlabeled data to support the learning model. In this scenario, we can use a self-taught learning pipeline. First, we train the feature model with the learned image label pairs. Then, we inference the stu labels for unlabeled images. We can further train the feature models with these stu labeled images. And this is the self-taught learning pipeline. The core problem is how to ensure the training with stu labeled images is trustworthy, that the retraining will not damage the capacity. However, it is hard to do as the stu labels are very noisy. We will use the proposed ICI to ensure that this selection is credible. We first encode the images into features. Then we train the linear classifier with the labeled image label pairs. The labeled images are inferred by the trained linear model. To select a credible subset to expand the training set, we use the proposed ICI to identify noisy data and remove them from the selected subset. Then we can retrain the classifier with these two labeled images and repeat this process until all the data are selected. As we introduced earlier, we model the featured and one-hot pseudo-labels with the aforementioned linear system with noisy indicators. Then we solve this system and simplify this to a single standard linear regression of noisy indicators. However, popular approaches to choose lambda are not suitable in our case. We thus generate a solution path to better identify the noisy data as visualized in this figure. We can further extend the sparse learning framework to logistic regression case. Similar to the linear regression case, we introduce a noise indicator to the linear predictor. Then, with simple transform, we can get a standard logistic regression model with extended coefficients. Thus, we can use popular optimization algorithm to solve this model. Here we check whether our theory and empirical results are matched. In more than half of the experiments, the assumptions C1 and C2 are satisfied. This is a success key to the success of ICI. Most of them will achieve better performance after self-taught with ICI. When all the assumptions are satisfied, we will get better performance in a high ratio. Even if C2 and C3 are not satisfied, we still have the chance of improving performance. We can further use this linear system in the problem of learning with noisy labels. Learning with noisy labels aims to learn a robust model from noisy training sets. We combine the aforementioned linear system into learning the recognition model with noisy training set by iteratively do the feature learning and sample selection stages in the training time. In the first stage, the network is trained with cross-entropy to extract features and classify labels. As there are noisy labels, the network is not well trained. To solve this problem, we need to identify noisy data and remove them from the training set. We assume a linear relation between the features and one-hot labels, and those break this assumption will be identified as noisy data. We solve this linear model with sparse bounty on the noisy data indicators. With a solution path, we rank the data by their selecting time and remove the identified noisy data. This ends the second stage, sample selection stage. Then we return to the feature learning stage and repeat the two stages iteratively until converge. To make the linear system scalable to large datasets, we first compute the class similarity matrix and divide the most dissimilar classes into groups. For each group, we select a small number of training data to construct small pieces of data. Then our model is run on each piece in parallel. To encourage the linear relation, we can append the sparse penalty on the output of the FC layer to get a sparse output. To further exploit the support of noisy data, we combine our algorithm with Kinetics and regard those data as unlabeled data to generate new training data. We test the label precision performance of our algorithm to check whether we can distinguish clean data from noisy data. It can be found that in different settings, we can consistently achieve high precision, showing the capacity of noisy data detection of our algorithm. That's all. Thanks for listening to the talk.